Welcome to this video on limits. So in a previous video we studied the diameter of the pupil of some animal under the influence of light. So if there is a lot of light then the pupil shrinks, and if there is little light, if it gets very dark, then the pupil becomes larger. We already saw that we needed some new mathematical machinery to deal with those kinds of situations, limits. And in this video, we'll focus a little bit more on limits and say some more about that. So let's have a short outline of what we will see. I will start with an informal definition of a limit. So if you want to talk about limits in mathematics in a very strict way, you need quite a bit of machinery that we're not going into. So we'll have more of an operational view of how to deal with limits. Then we'll also get to one-sided limits, and that may sound complicated, but it basically means that if you have a difficult point, say 0, that it can have an influence whether you go to 0 from the right, so with positive values, positive small values, or from the left with negative very small values. I will say a little bit about computation of limits, and some limits you can deal with using what is called the squeeze theorem. So let's see. First, an informal definition of limit. So the notation that we use is this here. And you read this formula as the limit of x going to a of fx equals L. So the limit of f of x as x goes to a equals L. And what it means is that if you choose x very close to a but not equal to a, and that is crucial, so close to a, not equal to a, then fx can get arbitrarily close to L. So basically, if you want to have fx minus L, the distance between fx and L, so absolute value of fx minus L, you can make that as small as you want. So if you want it to be less than 1,000, less than 1 over a million, less than 1 over a billion, you can achieve that if you choose x very close to a, but not equal to a. And the not equal to a is important here. So let's look at maybe a too simple example, but still I just want to explain a little bit on how this works. So let's consider as an example the function f of x equals x squared minus 4 over x minus 2. Now, if we consider this function and say that we would like to have its domain, so for which x values is this defined? So the domain of f is, well, basically every number as long as we don't have division by 0. So we should exclude 2 from the domain. Because if you plug in 2 and if you just look at the denominator, x minus 2, you would get division by 0 and the function does not exist. So this is the domain. Now, if you want to plot it, so say that we want to plot the graph of this function, then you hopefully see that we can rewrite this. So I can write the numerator as x plus 2 times x minus 2 and then divided by x minus 2. And you see that as long as you stay away from 2, there is no problem at all. And the function, in fact, is just equal to x plus 2. So a straight line, slope 1. So if you would like to plot this thing, then you get x-axis, y-axis. At 0, the function equals 2. At 2, it doesn't exist. And it crosses the horizontal axis at minus 2. Yep. So we get, well, we get y equals f of x, but at plus 2, there is a hole here, there is a gap in this graph. So I draw that with a little open circle to indicate that that is not a part of the graph here. Because the function does not have 2 in its domain, there is no function value here, so there's a little open circle here. So the graph of the function is basically a straight line, but one point is missing in that straight line. Now, of course, it is clear that if you approach x equals 2 from the right, if you pick values very close to 2, or you go from this direction, so it doesn't really matter if you go less than 2 or bigger than 2, but you can have f of x as close to 4 as you like, because that would be the value here, right? This value here would be 4. But that one point is missing from the graph. So what we can write down is that the limit x is going to 2 fx, that does exist, and it is equal to 4. So because in the limit, as it says here in the definition, we take x very close to a but not equal to a, we miss that crucial point, and we just find that the limit of x going to 2 of fx equals 4. Let's do one more example. And let us consider the function, so different example. And let us consider the function f of x is 1 over x. Now, a very simple formula, but you know, of course, that it's not defined at x equals 0. And if you would make a plot, x-axis, y-axis, then you can probably sketch that yourself with what you have studied in high school. It doesn't exist here. And if you let x go to infinity, it goes to 0. And similarly here, so this is y equals f of x. It's a hyperbola, and it has 4 asymptotes, or 2 asymptotes depending on how you choose. But if x is going to infinity, the function goes to 0. So for very large values of x, the function goes to 0. If you let x go to 0 from the left, from this direction, you see that the function itself goes to plus infinity. If you let x go to 0, but in this direction, then you see that the function goes to minus infinity, and here the function goes to 0 again. So from the graph, you can read off that the limit of x is going to infinity, 1 over x equals 0. The same holds if you let x go to minus infinity. If you let x go to 0, but then from the right, and we will write that like this. So x is going to 0 from above. The values of x are close to 0, not equal to 0, and bigger than 0. 1 over x, you see that you get plus infinity. And if you let x go to 0 from below, we get minus infinity. So we will introduce this notation properly, but I want to convince you that this idea is quite intuitive, what is happening here. Okay. Now, this distinction that we make here, that we treat these cases differently, that leads to one-sided limits. So if you look at this function here, so here I have a function y is f of x, and you see that it looks like this for negative x and it looks like this for positive x. So many students find that confusing, but it's perfectly okay to say, well, I'm going to define a function, not a limit, sorry. I'm going to define a function, and let's call that g because we do something differently. And if I say, well, I want it to be sine of x for x less than 2, I want it to be x squared plus 3 for 2 less or equal x less than 3, and I want it to be, let's say, ln x, the logarithm for x bigger or equal 3. This is one function, and that's perfectly all right. So you can do it like that, and here I have something like that probably. So I have something to the left of 0 and to the right of 0. Now, if I want to say something about limits, I need to take this into account. So what you see in the graph is that if you approach 0 from below, so that means that we follow this part of the graph, then you see that we end up at 2. So the limit of x going to 0 from below of fx, and this is just a different notation, 0 and then a superscript minus, that's just indicating that we take values close to 0 but a little bit less than 0, then you end up at 2. So even though there is an open circle here, and the function is defined as -1, the limit, if you come from the left, from below, equals 2. And similarly, if you come from the right or from above, it is -1. And to make this even more, or even stranger, I'm not sure how you would like to say that. So what you could also do is have a function that does something like this. So open circle here. Below, it does something else again, and also open circle, and you can define the function value at this one point to be yet a different value. And if I say that this is 1, this is 2, and this is -3, then in this situation you would have that the limit x is going to 0 from below of fx equals 2, f0 equals 1, and the other limit, the limit x is going to 0 from above fx equals -3. So you can even have that situation. Now, probably you agree with me that this is very artificial, and also for many applications you don't really want your functions to have jumps. You would like them to connect. So even if you have like these different paths, you would like them to connect at 0. So often we will require that, and you will also get questions in which you have to choose certain parameters to make that so. But in principle it can happen like this. So the limit from the left, from the right, and the function value, they can all be different numbers. Now, in this situation, the one-sided limits are not equal, and that means that the normal limit, so if we don't write these special arrows or this minus and plus here, but if we write simply limit x is going to 0 f of x, then we say it does not exist. So if the two are the same, if this thing and this thing would yield the same number, then we say that the limit exists. And otherwise we say that it does not exist. So that's in the blue box here. So for this limit to exist, we need both of the one-sided limits to exist and also to be equal. Now, this was all quite theoretical. Let's look at a couple of simple functions and see whether we can compute limits there. If you're dealing with polynomials, we have already seen that polynomials are always defined. So the domain of a polynomial is every real number. So if you have a limit with a polynomial, the limit of x going to a f x, you can just substitute it there because it exists. There are no difficulties there. In a sense, polynomials are the simplest functions we can deal with. And then the next category are rational functions. And rational functions, as you know, is a polynomial over a polynomial. Now, since we're dividing by q of x, we need to exclude from the domain the points where qx equals 0, because division by 0 is undefined. And this already can lead to interesting limits. So several things can happen. So if q of a is unequal 0, you just plug in x equals a in the expression. So if you have the limit of fx, You just substitute x equals a and there is no problem. If it is 0, well, that gets more interesting. And let's look at a couple of examples to see what's happening here. So this situation is simple. I'm not going to talk a lot about that. But this situation where q of a equals 0, let's look at a couple of examples. So first example, the limit x is going to 2. X over x minus 2. So if you just plug in x equals 2, you should always try that, you get 2 over 0. And well, that doesn't exist. So if you pick numbers very close to 2, but a bit below or a bit above, the function will blow up. You will get very large numbers, and this limit does not exist. That doesn't go to a fixed number, so does not exist. So that can apparently happen. If the denominator equals 0, it can happen that the limit does not exist. Next example. If you take the limit of x going to 2, and then x squared minus 4 over x minus 2, well, that was my introductory example. So you can write it as the limit x is going to 2, x plus 2, x minus 2 over x minus 2. Now, this limit thing, it means that x is close to 2 but not equal to 2. Since it is not equal to 2, I can strike these and write 1 instead. So what we get is the limit x is going to 2, and then we just are left with x plus 2, and then I can plug it in and I find 4. So here it exists. And then finally, limit x is going to 2, x squared minus 4 over x minus 2 squared. So here I can do a similar simplification. X going to 2, so I'm going to write x plus 2, x minus 2, and here I have x minus 2 squared. So again, I can divide by x minus 2, so I get a limit x going to 2, and what we are left in the numerator is x plus 2, and the denominator x minus 2, because I've got 1 left. There is a square here, so the square disappears. I divide here and then the square here goes, and I'm left with 1x minus 2. And you see that if I plug in x equals 2, we have division by 0, and the thing doesn't exist, so does not exist. So you can have several situations for rational functions. One of the things that we can observe, so we have px over qx. For the first example, we have px, the numerator, equals x, and p2 is unequal to 0. Here in the second case, we have px is x squared minus 4, the numerator, and you see that p2 equals 0. And if you want to have any hope that the limit exists, the numerator should also be 0 if the denominator is 0, because then maybe you can divide out one of these factors. But it's not guaranteed, because here we have px equals x squared minus 4, so also p2 equals 0, and yet the limit does not exist. So it is not sufficient. It is necessary, but it's not sufficient, it's not enough for the numerator to be 0. Another category of functions that we can consider are limits where we have roots. So first, a general theorem: if you know that this limit exists, then if you take the nth root of the function fx, that goes to the nth root of the original limit. Of course, if n is even, you need L to be positive, otherwise this is not going to work. With square roots, we often have a trick that we use, which is called rationalizing. And what you can try to do is, if you have an expression with 0 over 0, you can try to rewrite the expression. And here is an example. So here we have this limit. And if we just plug in x equals 0, you should try that first. If you get a number, then you're done. But here you see that we get square root of 2 minus square root of 2, that equals 0 over 0, and 0 over 0, that can be anything. Now the idea that we are going to use here is, in the numerator, we have something minus something. So if I focus a little bit on the numerator here, you could see this as a minus b, where a is the square root of x plus 2, and b is the square root of 2. And what I'm going to do is I'm going to multiply this with a plus b. And the reason is that this equals a squared minus b squared. And sometimes that gives a nicer result. So let's see what happens here. So I'm going to multiply with this number here. That's the a plus b. But if I don't want to change my result, I should not only multiply the numerator, but also the denominator with this number. And then I'm multiplying the whole expression with 1. And if you multiply something with 1, it doesn't change. So here in the numerator, if I multiply this out, I get a squared minus b squared. So I get a squared minus b squared, and the product disappears. And you see I'm just focusing on the numerator now. So a squared is x plus 2, b squared equals 2. And you see that I have x minus 2 plus 2, so that just gives x. So that simplifies a lot. And here in the numerator, I just write this product here. And now what we have found, here we have x. In the denominator we also have x. So I can divide by x. It's the limit of x tending to 0, so x is close to 0, not equal to 0. So I can divide that out. And then I have this limit. So I have rewritten, I've just done a ton of steps to rewrite this limit. And now I can simply plug in x equals 0. Because if you do that, then we find this number here, and apparently that is the limit. So indeed, if you would plot this expression close to 0, you would see that the values get close to 1 over 2 times square root of 2. So the idea of this trick, it's simply a trick, this rationalizing, is to recognize that you can use something like this. You see a minus b, you multiply with a plus b, or you see something a plus b, where a and b can be anything, and you multiply with a minus b. Let's do one more example. So here I have this limit, and again the first thing you should try is just plug in x equals 25. Well, we get 0 over 0. That doesn't really help. So what I'm going to do is I'm going to multiply this thing with square root of x plus 5. So that's the idea. So we multiply the denominator, this is the denominator, with square root of x plus 5. And the reason is we have something of the type a minus b times a plus b then, which is a squared minus b squared, which is x minus 25. If you do that, if you multiply the denominator with that number, you should also multiply the numerator with it. So here's where we did that. And again, you see that a small miracle appears. So these problems that we give you, they are carefully constructed, because now you can divide by this number, because it's the limit. So x is unequal to 25. You may divide by x minus 25. And then we end up with this limit, and this one is trivial because here you can simply plug in x equals 25 and you find the square root of 25, which is 5 plus 5, and the result 10. So try to be aware of these types of expressions and this trick to do that. So finally, for some standard functions, we didn't talk about sine, cosine much yet, but if you have a limit of the sine, you can simply plug it in. Same for the cosine, exponential, and the logarithmic function, and the last one, of course, provided that the argument is a positive number. And then to wrap up this video, the last topic is the squeeze theorem. And the squeeze theorem is an extra tool to find some limits. So let's first look at a theorem that may seem complex at first, but it's pretty okay. So let me guide you through this. So the idea here is that we have a limit with a function gx that is difficult. So what we are trying to find is, for the blue function, we are trying to find the limit x is going to a g of x. But g of x is a difficult function, so we cannot directly do that. Now the idea is to find a black curve fx, a red curve hx, such that gx is always in between f and h. So we're basically looking for a lower bound and an upper bound, such that the lower bound and the upper bound, it's easy to find the limit. So it's easy to find the limit of x going to a of fx and of hx of the upper bound. And if they are both equal, then because this g function is in between them, g also needs to go to L. So if you look here on the plot, if g is in between the black and the red graph, and the black and the red graph are at x equals a the same value, then also the blue one needs to have the same value. So sometimes you see as a name also the two policemen and a drunk theorem, because if you have a drunk man and there are two policemen on his or her side, and the two policemen walk towards the police station, then also the drunk has to go to the police station because he is squeezed in between the two. So that's the idea here. Now, this is the theorem, so how can you actually use that? How do you use this in practice? Let's look at an example. So here we have the limit, x is going to 0, x squared times cosine 1 over x. This one we cannot tackle with the tools we have seen so far. So if you should always try to have a little feeling of what's happening there and where you think this limit is going, because if you already have a clue, some intuition what the limiting value is, that can help you greatly. So this thing, x squared, well, that's going to 0, of course, for x going to 0. 1 over x, well, that's not defined for x going to 0. But then a cosine function is always in between -1 and +1. And that immediately gives you, if this is the g function in the theorem from the squeeze theorem, so the squeeze theorem we just had, squeeze theorem. So our g function, the complicated one that we would like to find the limit from, that is x squared cosine 1 over x. And then we're going to use that this thing is always in between -1 and +1. So we needed fx less or equal gx less or equal hx. For the f, we need the lower bound and we set the cosine to -1. So this is going to be minus x squared. And for this one, we take the upper bound of the cosine +1, and this is going to be x squared. And then if you let x go to 0, this limit for x going to 0 is simple, equals 0. This one for x going to 0 is also 0. So then the one in the middle also needs to go to 0. So that's the idea. So let's try to write that down properly. So what we have here is this is just to help you understand. This is the function gx. So you see that it goes like a cosine, but when you get close to 0, it starts going up and down a lot. then the limiting values, so the cosine is always in between -1 and +1. And that's true for every x as long as you stay away from 0. So what I'm going to do now is here to write it down. I multiplied all three of these things with x squared, and x squared for x unequal to 0 is a positive number, so then the inequality sign stays the same. And you see that this is our function gx, this is the lower bound fx, and this is the upper bound x squared. So I also plotted them, and you see here that indeed the lower bound in black, that is precisely below the graph here. The upper bound in red it just encloses the blue function. And now we can use the squeeze theorem. So we know that fx goes to 0, hx goes to 0, and then the squeeze theorem tells us that also the middle function gx has to go to 0. So that is how you can use this squeeze theorem. You have a function, and the function basically close to 0 cannot move. It is enclosed by two functions that both go to 0, so it has no other option than also going to 0. Let's do one more example. So here we have the function, and now pay attention, the limit is going to infinity. So x goes to infinity, and then again to get an idea what's going to happen, this sign is always in between -1 and +1, and both -1 over x for x going to infinity goes to 0, and +1 over x for x going to infinity also goes to 0. So we are going to use that. So here's the graph of the function, and now we're interested in what happens if x goes to infinity. So if you get bigger and bigger values of x. So the sign is always in between -1 and +1, just like we had before. So we have this inequality. Now x is going to infinity, so I pick x bigger than 0 and I divide the whole inequality by x. This is our function g of x. So this is going to be the lower bound f, and this is going to be the upper bound h. And both the limits of f and h for h going to infinity are simple. Here I plotted the upper bound in red and the lower bound in black. And again we use the squeeze theorem. We know that f goes to 0, h goes to 0, g is enclosed by them, squeezed in by them, so it also has to go to 0 for x going to infinity. That brings me to the end of this video, so let's wrap up what we have seen. We looked at the definition of the limit of a function. We have seen that sometimes you need to make a distinction whether you go to a difficult point from the right, from above, or from the left, from below. We have seen a couple of tricks to compute the limits, and in particular we have seen the squeeze theorem to find some limits that we could not do using the previous tools. That wraps it up. I hope everything was clear. If not, let me know, and otherwise I'll happily see you in the next video.